Thank you, everyone, for joining in the very embarrassing birthday song. This is an appropriate title for after the lunch break. Hope you're all fed and watered and whatnot, and hopefully you're not too bloated. I had a very quick lunch, so I am feeling a little bit myself. But today we're going to be talking about breaking the bloat of the web. And our mission today, should you choose to accept it, is to achieve the fastest possible navigations on the web. So my name is Townsend. I'm a principal product manager at Cloudflare. I've spent over a decade at this point, I think, working on web performance. I joined Cloudflare back in March to take over responsibility for our real user monitoring product. This is something that you can use completely for free. You don't even have to be a Cloudflare customer. You could use another content delivery partner. You can just install this on your site. And I'm not doing that as kind of like a sales pitch. But like Jack mentioned this morning about making sure that we're kind of measuring the impact of AI and things like that. You want to be measuring the fact that you aren't making things worse in the kind of performance world. So this is one way to do this. So whether you use my tool or anyone else's, please do have some real user monitoring, because I can almost guarantee it will be enlightening to you in terms of the data that you'll see in there and the experiences that real people have on the web. And I joined Cloudflare specifically to work on this product because I love the web. I think it's a real gift to the world. We can write once, deploy everywhere. Literally within seconds, we can reach a global audience on most devices. And there's like nowhere else in tech can do that. And outside of tech, it's even worse. You can't just go and roll out a new release to a bridge. It's going to take a long time to go and make those changes. So we can see the impact of our changes just within seconds, and that's amazing. But unfortunately, the web has a JavaScript problem. For my entire career now, it's my 38th birthday today, and I started, I think, in web dev when I was 14 or 15. I think I was working by the time I was 16. So, 22 years. It's been a long time. Basically, JavaScript has been a problem the entire time in different ways. Early on, we just didn't even know how to measure it, so it was we were somewhat blind to it. But back in the days when websites took a long time to load or would crash a lot, you could kind of feel that on your machine because your clunky old desktop was the same as everyone else's clunky old desktop. And nowadays we have this broad spectrum of devices and different contexts that real users experience the web with. And JavaScript is growing faster than any other resource, which is obviously compounding this problem even further. My colleague Tim Cadleck recently ran the numbers. He was looking for what levels of growth and what periods we saw this in. And he found this 10-month period where we saw 15% increase in JavaScript on desktop and 10% on mobile. And that was across both the 75th and the 90th percentile of websites. So the slowest 25% or the biggest 25% and the biggest 10% or slowest 10% got even slower, or even heavier, should I say. And his theory was that, if you look at the dates of when this started to happen, it's LLMs kind of driving this into our industry. But it's not just purely LLMs. You can look back. This is the HTTP archive. Looking back over a decade, and you can see it's always kind of steadily been increasing, and it's kind of starting to go up at a bit more of an exponential rate now. So if we look back over a decade, we can see that our JavaScript has grown almost three times in size over 10 years. A quarter of websites are now over 1.5 megabytes of JavaScript, just in terms of loading a page, and 10% are now over 2 megabytes. We can compare that back to the size of Doom back in the old days. This is many floppy disks of data, and this is the transferred size, not even the uncompressed size. So after it's gone over the network and we've actually delivered it into a browser, then the actual device has to execute this. Once it's decompressed, this might be 10, 20 megabytes of JavaScript that we're kind of inflicting. And the bit that really perplexes me, and I really can't stop thinking about, is what are we doing really that's so much more interactive, that requires all of this JavaScript? What are we building that's new? If we look at the web's greatest hits in terms of different user experiences, obviously AI's come in, but, the kind of chat interfaces have been, they've been on the web for ages. We're talking back to like the 90s even. And so effectively, the majority of what we're building is some kind of iteration or variation on things that have been part of the web platform for a decade or even more in many cases. So these aren't unsolved problems, and we should be getting better at delivering those. So why is this all such a big deal? I care about this. Why do I care so much about JavaScript? Well, byte for byte, JavaScript is the heaviest of all resources. If we think about loading web pages and things like that, HTML downloads progressively and is streamed down into the browser, and it's useful throughout its journey. We don't have to have all of the HTML. We can discover sub-resources, your images, your videos, your CSS style sheets, all the other bits that compose a website. We can discover those as the HTML is arriving. You can think of it kind of like loading a progressive image, where you get the blurry version when a few bytes have arrived, and then it kind of becomes more and more crisp as you get more of it. And similarly, we can render that HTML. We don't need the entire page. The browser can start to render it and show you the kind of viewport like above the fold effectively as that's downloading. Whereas with our JavaScript, it's effectively not useful to us until we've downloaded the whole file. And then when we've got it, while our videos and our images can decode on a separate thread, often they'll be GPU accelerated. There might even be dedicated decoding hardware. If you've got like an iPhone or a Mac or something, there's chips in there that are specialized around certain different codecs. JavaScript fights over the main thread of our CPU, so you can kind of imagine what happens there. And then this is all compounded even further when we try to optimize this stuff. So we take all of our JavaScripts, typically, and we'll bundle them together to try and increase our compression ratio. So by having a lot of duplication, we can get files smaller, and that's how things like gzip works and Brotli. But this means that we might not need all three of these files for this one page load. We might not need them all right at the beginning during page load. There might be things that could come further down the line. And we're forcing people to just download this straight away, whether they need it or not. And then we still have to parse and compile. Even if we don't execute it all, we still have to load that into the actual execution context. And what this all results in is this kind of uncanny valley, as it was a name that was given to it by Paul Lewis from Google, I think over a decade ago at this point, where effectively you can see the page, but you can't actually interact with it. So you start clicking and tapping on things, and it's just not responding. It's incredibly frustrating. And you might be thinking, well, yeah, okay, I can see how we're dumping all of this stuff into these devices, putting more pressure on the network. But, every year Apple released a new iPhone, right? And things are getting faster, and we've got 5G now. We're not still on 2G and everything like that. Yeah, it's not really working out like that. This is some analysis from Alex Russell of Microsoft, kind of looking at the kind of benchmarking specs of the devices that typical people might be buying. And yeah, if you've got the latest iPhone every single year, you just about kind of keep up with that. But that's a device that's on full power. It's not sat on low battery mode or anything like that. All the cores are firing. It's got a great connection. And who buys? I mean, some of you might be baller enough. I love my tech, but I don't buy the brand new iPhone every single year to keep up with this stuff. And even when I do, I still experience these scenarios where I get, a website's loading slow, or, the interactivity hasn't caught up with me browsing around. That shouldn't happen. But the important thing to note about this chart is that these kind of flagship devices at the top two sections, are just about kind of keeping up. But 2/3 of purchases happen in devices down here. These are the ones that very much aren't keeping up. And if we look at the latest Galaxy A26, I mean, it's from last year, so it'll need updating, but that has the same power as an iPhone 8. I think it was 2017, so we're talking almost a decade ago. 2/3 of devices fall into these bottom two categories. So we're shipping almost 3 times the volume of JavaScript to devices that simply can't handle this. So in summary, like, even if your visitors are baller enough to be buying the latest flagship mobile every year, which is exceptionally unlikely, we appear to be still at the whim of Worth's law, which basically describes how our software demands are growing faster than our hardware capabilities can keep up. So this would be a very negative talk if I ended it at this point. So I'm not here to outlaw us using JavaScript or anything like that. The web will be a much more boring place without all that interactivity that it provides. But I'm here to question if we're kind of being honest about the cost and really interrogate where we should be using it. Because the good news is that the web platform is fighting back and has been quietly fighting back for years. Many of us just choose not to pay that much attention. So we've had things like HTTP2 and HTTP3 that have reduced the overheads of serving like small individual files and getting that kind of granularity of when do we need to load these things. But if we actually look at, I don't have a chart for it today, but if you actually look at the adoption of moving to many smaller files, it's very, very slow. And that's largely because of needing that increased compression. We don't want to serve all these files individually and then have much larger kind of network transfer because they don't compress as well individually. We've had things like Bloat introduced, and that's been seen massive adoption over the past decade. It's been in baseline for a long, long time, and that gives us about a 30% kind of additional compression at best over gzip. And obviously we have other tools that are continually trying to give things like HTML more and more power to help guide the browser to be more performant. So things like fetch priority and resource hints, where we can tell the browser these things are important to our loading process. And HTML and CSS are continually eating away. Like on one of Jack's slides, he had, telling the AI that it should use a dialogue element. That's something that traditionally would require JavaScript, often a big library, because it'll bundle in all of this different functionality. And it's just one element now. So they've been eating away at JavaScript. It's a bit weird how JavaScript's growing, despite the fact that more and more can just be done with HTML and CSS. And I think it's really worth investing in this platform knowledge, like something that Jack covered, because very few things on the web platform actually end up getting deprecated. There's things like, I think, like the blink tag and the marquee, about the only ones really that have gone from HTML. So this is something that you can depend on for the long term. There's a bit of a melancholy phrase, and I'm sure there'll be some parents in the audience who have maybe seen this kind of quote where it's like you can't remember the last time you picked up your child. There will be a point where it's the last ever time you pick them up, but you won't know at the time. You'll look back on it one day maybe. And I think this is the same thing with jQuery. There was a point at which I didn't need to use it anymore. I don't know when it was. I just stopped using it, and that was the last time. And that knowledge is. There might be some case where that becomes useful if I'm investigating some sort of legacy application, but chances are that knowledge is utterly worthless to me now. Whereas all of the stuff that I've learned on this 22-year journey with the web, is still, the vast majority of it is still valuable today. So I want to look a bit more forward into the future and look at some APIs where the web platforms evolving and again trying to support us with these rich user experiences that we want to provide to our users. So I've mentioned Bloat and gzip, but these kind of regular compression mechanisms can only take us so far. There's a new technology built into Chrome that I'll explain in a second, that my colleague Alex did some analysis on. So he took a file that was 272 kilobytes in size. He compared that with gzip, and he got it down to 92 kilobytes. So a good amount of kind of duplication in there. He didn't actually test Bloat, but I just assumed for this figure that Bloat's at its general best case scenario where it's 30% better than gzip, so down to kind of 64 kilobytes. But with this new technology, we can get down to very, very minute file sizes. So we can start to undo some of that damage. And the great thing about this is that when it's this good compression, you might have heard that Bloat is very CPU intensive. So if you try and use those max levels of level 11, And the browser, the CPU has to really churn through that content and reanalyze it to try and make the file as small as possible. You can't really do that for like dynamic content because you'll add so much latency to serving that file. With this, because the file sizes are so small, you can set even like level 1 compression, barely anything on the CPU to compress it, and you still get tiny file sizes. So this means you can use this for dynamic content as well as static content. And it doesn't just affect the actual bandwidth that we use. We've seen, again, Alex has done a report on this, we've seen this actually impact our latency as well. So, when we've got to go all the way back to your origin, go and request a file, we can see that actually gets delivered to the browser faster than gzip has even started transmitting, because the piece between the origin and the content delivery network is so much faster as well. And he's built, if you want a visual demo of this, there's a great website he built called canIcompress.com. You'll need to use Chrome for this. But effectively, every minute, it will redeploy, and it'll have a new visualization. And they built a whole handful of different visuals. And you can see here, it will tell you how much data it transferred. So on this release, 400 bytes for a whole new visualization. So we can get them really, really tiny. So before I explain what this technology is and how you might want to use it, this isn't an excuse to just go away and use more JavaScript. Obviously, it means that you can send more and have less impact from it over the network, but we can't forget about the actual execution side of that JavaScript as well, and that's where the following two APIs that I'll take you through will be really helpful as well. So, I don't want to see this. This needs to start going the opposite direction, or at least just leveling out. That would be great. So this feature is called Compression Dictionary Transport, which is a bit of a mouthful. If you want to just call it compression dictionaries, that's fine. Last September, it became an IETF proposed standard. So like I said, it's built into Chrome now, well supported. And effectively, what it allows you to do is take one resource, typically a text file of some kind. It could be HTML, CSS, JavaScript. It could be a standalone, just plain text file. And you use it to compress another file. So this is kind of what Brotli does internally, is it has its own dictionary, and that's how it gets those benefits over gzip. But you can't, until now, control that kind of internal dictionary. So you can't tell it what are useful words or HTML elements or CSS attributes, all that kind of stuff that you're using. You can't instruct it to use that for compression. And the reason why we might want to use this is kind of twofold. Firstly, if you're doing continual releases like every day, every week, that's wonderful. Try and get them out there, get that value into your users' hands. But each time you do that, you effectively break the cache sat on that user's device. So if someone's browsing your website and you do a release, they're going to have to re-download all the JavaScript, re-download all the CSS, and all that kind of stuff. And obviously, that's very expensive. Those files come down full size all over again. Even with that compression, that can still run into hundreds or even megabytes of JavaScript. But this allows you to just do an upgrade. So you can think of it more like a diff on GitHub, where you just see the changes, and that's all the browser needs to ship down, because it knows you've got version 1. Here's the difference between version 1 and version 2. I'm going to send you that. And then it actually compresses that diff as well. So that's how we get those really tiny files. And what it allows us to do is compress across files this way as well. Because if we know that all these, say, 10 files all contain the same words and phrases, because we can use one text file, for example, to compress all of those things, we can share that compression across all of them. So you can serve individual small files and still get high compression ratios. And the way that we do this is just a few HTTP headers. It's not actually that simple. There's a little elbow grease, and I wrote a blog post back in December that you can check out to learn all about my journey implementing this. Effectively, the challenging part is actually applying the compression. But in terms of the browser workflow, it's a fairly straightforward process, so I'll explain how to do that. So this is something that Shopify are using. So they're using the upgrade mechanism. You can pop open DevTools on the checkout, look at their JavaScript files, and you can see they've got this kind of random hash which is effectively a proxy for the version number in the URL. And then you'll see that there's a header called users dictionary. So this is telling the browser, oh, I've just stopped my presentation. Sweet. It tells the browser, keep this file and use it as a dictionary for the future versions that match this URL. So you can give it whatever URL you want. You can match certain directories or different types of content as well. So you could say target all style sheets if you wanted to. But effectively, they're doing this for upgrading their JavaScript. So each time you'd have to re-download that. And the way that this works is your browser, first time accessing Shopify checkout, makes a request that says, give me version 1 of this JavaScript file. And it says, I don't have a dictionary or anything like that. So the server goes, OK, yeah, here you go, here's version 1. It's just regular compression, Brotli, etc. And that's why it's still important that you do still implement like the basic compression without these things. And it'll serve that file and say, hey, just store this as a dictionary as well as using it to actually execute that JavaScript. Imagine another release goes out, and then someone browses to the next page, and the new page has version 2 in the HTML. So now when the browser requests that, because it's got version 1 stored as a dictionary, it can tell the server, hey, I've got version 1, here's the hash of that file, so that way you know it's exactly the right contents. Can you give me the dictionary? And it will tell the server, hey, you can compress this in those dictionary-based formats. So that's where you see the DCZ. The server will then compress that file using that dictionary. So this is one kind of challenge with implementing this, is that your server needs to maintain a copy of the dictionaries that it's used. So it'll retrieve that dictionary, compress that file, probably cache it, because you don't want to just recompress that file over and over and over again, even if it is fast. And then it will serve that version 2, and it'll be just that little diff that's been compressed, and it'll be a few bytes. Obviously, if you've done a bigger change, then it will be bigger, but if you've just literally bug fixed one line, then that's all it will be. And in order for this to be the most efficient, like I said, if you want that diff to be as small as humanly possible, so imagine you are doing some bundling, you've got all these different files, all these kind of chunks of JavaScript. What you need to ensure is that each time you do a build, it's kind of deterministic, and what happens is when you do a release, it doesn't swap around which modules are in which files, because then obviously you're going to get much bigger diffs. So you need to make sure, I know that Vite does this correctly. So if you're using Vite, then you're in solid hands. If you're using things like Webpack, I'm not sure. I don't know if there's a version that does that now. But keeping your kind of bundles or your chunks stable is really important. And then Google Search are implementing the kind of alternative view, which is to use something more broadly for compressing different content. So rather than upgrading the same file, when you load a Google Search page, you'll see that it's used as a dictionary for literally everything. And the reason why they've done this is obviously they want to get this down to like the smallest amount of latency possible. And previously, they would host their Google logo as a separate SVG because they wanted to share that across both the search page and the results page. Whereas now, they can embed that so they don't have to wait for a round trip for that to download. It can literally just be sat in the HTML. And even though it's duplicated in the results page, it's compressed using that original page as the dictionary. So effectively, the second page has a reference to the logo in the first page. And again, you can see that you'll get this response type of DCB here. So they're using Brotli rather than Z-standard to compress this. It's all public, so you can go and check it out. And to show you a bit of an impact, I implemented this on my personal site. If you go to like the home page, for example, then navigate to another page, this is my events page, you'll see that in Firefox, which doesn't support dictionaries yet, I get like a 21 kilobyte download. It's not massive. And I get like an 85% compression ratio on that. So not the worst experience. Obviously, there are bigger sites. This is just an example. But if I navigate to that with Chrome, using a dictionary gets it down to a quarter of the size, so 5 kilobytes. So you can see what kind of thing is possible here. And for reference, HackerNews, which is like famously one of the most lightweight sites on the internet, is 6.3 kilobytes. So I beat HackerNews on how lightweight navigating my site is. So if you want to implement this kind of dictionary compression, What you effectively need to look for across your pages, you can do this literally by hand. You don't have to automate this as part of a build process. Obviously, the bigger site you run, you probably might need to. But you just look for commonalities between these pages. So, on an e-commerce site, you might have like a homepage template, product listing template, product detail page. The mega nav at the top and the burger menu and all that kind of stuff is all going to be duplicated across all of these pages. It's likely to be about the same, if not exactly the same. So what you can do is just extract that into a text file and then tell the browser to load that as the dictionary, and then as it browses around the site, it will use that dictionary to compress those pages. So we can kind of think of this as bringing the kind of single-page app kind of lightweightness in terms of navigation to multi-page apps, because effectively, single-page apps, you get the shell. You might do some server-side rendering, so there could be content between that, but effectively, you've got the shell, and then when you click on a link or submit a form, it goes and makes a JSON request, and then it populates that shell with the content after it's built it. We can achieve the same thing now with multi-page apps. You have your shell, which is effectively your dictionary, and then when you load the next navigation, effectively is just loading a diff between that shell and effectively just loading the content, and then the browser assembles the new page. And it's literally as simple as this. So you have a link tag that says, hey, this is where my dictionary's at, and the dictionary needs to respond to say what content it can be used for. So in this case, I'm just saying match on any document request, so any HTML request. Simple as that. Obviously, you've got to implement all the compression on the server side, but that's very different in different environments, so I can't go through all that today. So when can you use this? So at the moment, it's only in Chrome, but remember that this is a progressive enhancement. You still need Brotli, gzip, etc. So there's no reason to not implement this today, because you can impact over half of web users today and get that benefit for them today, and then as the other browsers catch up with their support, I think Firefox is pretty much done. They've literally created an issue ready for releasing it to the public. So you can see that in their bug tracker. And I believe I saw Safari have pulled in the tests into WebKit. So they're working on it as well. So it's probably by the end of the year, I would imagine that we've at least seen Firefox, and Safari will be well on its way, if not delivered. So we can give that power to so many people. And if you're interested in what our plans as Cloudflare are with shared dictionaries, you can read all about them on this blog post by my colleague, Alex. So I did say the fastest, and that is all sounding fast, but we can improve on this. And the challenge for me is okay, if we've got a single-page app, it's running in a browser, and it doesn't even need to make a network request. If you click a link and it re-renders something, can we beat that? And there is a way. So the next API is speculation rules. These are really exciting. We saw an absolutely amazing result by implementing these. So when we rolled it out to Cloudflare customers, we saw an average reduction in largest contentful paint, which measures our load time of a web page by 45% when we have a successful prefetch. So an amazing improvement on load time there. And what these do is effectively they provide a declarative API for prefetching HTML documents, so the kind of next navigation, or even completely pre-rendering that next page. And that's where we get that amazing kind of instant page load. So we want to try and hide as much latency from our end users as possible. And the way that we do this, tiny little bit of JSON. This is as simple as it can be. You can drop this into your page, and effectively you can match this on CSS selectors. You can give it a static list of links, or you can match on certain URLs. So you can give it a format like /products, and it will look at all of the links on the page and figure out when to either pre-render or prefetch those based on there's this eagerness setting that I'll explain. So I've got a little kind of video demonstration here of loading my site. This is loaded over a slow 4G, so you can see it takes a little while to download that first page. You can see the images are slow to load in. But then when I click on one of my pages, you can see you just get that instant load. There's a bit of a transition there because I've implemented another thing that I'll talk about in a second. But the pages just load instantly. And in Chrome, if you use the DevTools, you'll see there's this little green widget that appears just here to find the successful speculative loads on that page. So you can validate your approach that way. And the way that this works behind the scenes is you can imagine it like two browser tabs. So the browser, when we're doing pre-rendering, the browser's opening that second page in a new tab, hidden away from the user. So effectively, they kind of imagine them kind of overlapping like this. And then when you click the link, it just goes boom, instant switch. So that's the absolute fastest rendering you can get on the web. It's already happened. So friend Barry Pollard from Google literally said this is faster than any client-side rendering, even when it's not making a request. So this is the absolute fastest. The only trouble with pre-rendering is that it can be very wasteful and expensive. Obviously opening a second browser tab, executing all that JavaScript, etc., loading in any of those resources, when you may or may not actually click that link, is wasteful. And we don't want to put all of that bandwidth pressure on all of our users. You might overload your servers if it's a dynamic page. You've got to be very careful with that. And compression dictionaries might help alleviate some of that point. But we also can see issues with things like JavaScript executing. So if the analytics script running on that page doesn't detect that this is a pre-render, it might record that someone visited that page when they never actually did. So all of your analytics can get kind of skew-whiff. Most big providers have now implemented, they can detect this now, but if you have any concerns, then you might want to avoid pre-rendering. So our kind of first defense over that kind of wastefulness is the eagerness level. So you can go with most conservative. This waits until someone either clicks down on their mouse or is tapping on the screen. So literally in the 100 milliseconds between tapping down and lifting their finger off, we can trigger this prefetch or preload. So we're just trying to capitalize on that few hundred milliseconds there. So that's the most conservative. You're waiting for someone to actually tap the link. The chances are, other than in scenarios where they're like long pressing to like open a menu or something, chances are they're actually going to navigate to that page. You can step up to moderate, which starts to use a few more kind of heuristics in the mobile world. So it's trying to figure out what does it think they're going to click on. And the browser will manage all of this for us, so we don't have to concern ourselves too much. And on desktop, it starts to look at things like hover. So if you hover over something for a couple of 100 milliseconds, there's a good chance that you're going to click on it, right? Eager's the next level. That's just waiting for a very short time on hover on desktop. So literally, as soon as you are over there for like 10 milliseconds, it's going to assume that you're going to click on it. And then in mobile, it's looking for everything that's in the viewport that's been in the viewport for just 50 seconds. So if you're like swiping down a long page, it's going to skip over those ones. But otherwise, it's going to start prefetching. And then you have immediate, which is just as soon as humanly possible, when the browser is idle, please just start loading this next page. So you have to be very confident with those that someone's actually going to visit that page. And then our second defense is actually not using pre-render. I mentioned prefetch, where we literally just download the HTML. So that's far less resource hungry. It doesn't utilize the pre-parser, so it won't go and discover anything else on the page. So like your images don't download, videos, style sheets, etc. So you do get like an instant time to first byte. That HTML arrives immediately, as long as we've got enough latency as to when this speculation happened. But the rest of the experience has to still download when they activate. And there's a new option in the middle here called pre-render until script, which I don't really need to explain because it literally does what it says on the tin. It will pre-render that page until the first JavaScript is discovered in the HTML. So if you have one in the head tag, then it's just going to stop at that point, and it basically won't pre-render anything. But the important thing here is that the pre-parser will still run. So it'll go down all of that HTML, and it will discover anything else on that page and download that and populate the cache for you. So you can kind of balance these things. In terms of other results we've seen, even with conservative prefetch, which is the kind of least impactful option, Shopify saw amazing results on this. So across all of their loading metrics, time to first byte, first contentful pane, large contentful pane, they saw an improvement of 130 milliseconds on desktop and 180 milliseconds on mobile, and that was across all percentiles. So people on fast connections and people on slow connections all benefited from it. And then about a month ago, they stepped up from conservative to moderate. Obviously, they're taking their time to implement this and get it right. And they saw an additional 200 millisecond improvement across all of the loading metrics at the median. And while mobile is a little less impactful here, one of the really exciting things about this is that on desktop, at the medium page load, so 50% of people effectively get an instant time to first byte. So that means that by the time you click a link on a Shopify site on desktop, you've got basically a 50% chance that HTML already exists in your browser. And it can effectively, it still needs to download the images and things like that, but you're getting an instant server response time. So it's incredibly powerful. Now, while these are kind of super positive metrics, what they don't show is the waste. And that's why Yoav, one of the kind of implementers of this API, has now come up with a new measurement API to check that we're not just speculating and loading all of these things for people to not actually ever activate any of them. We don't just want to burn through loads of bandwidth for no good reason. So this is Chrome Canary only at the moment, but it's a very important thing that, I'm sure Yoav works for Shopify, so they're going to want it everywhere as soon as possible. Just a reminder here that, you can't optimize this stuff if you're not measuring it, and this is kind of currently like an area we can't see into. So in terms of kind of implementation, there are open public bugs on Safari and Firefox for this. It's in Chrome. Pre-rendered, they're a little more skeptical of because it's quite a challenging thing to implement. But hopefully we'll see some movement, at least with pre-render until script. You can improve the situation for over half of web users by implementing this, at least for Chrome. And the fallback for this is that simply these prefetches don't happen. People get a slower loading experience, but it doesn't break anything. So there's no reason to not implement this today. And if you're interested, we've got a product that will automatically implement these things for you called SpeedBrain. Again, feel free to go and check this launch post out. The only downside with this is that this is limited to kind of the traditional multi-page app or like regular website approach. It doesn't affect single-page apps. And a lot of the time, people have used single-page apps because they want that kind of seamless experience, and they don't want that kind of janky, old-school way of loading web pages. So can we achieve that, but without all of that JavaScript that we have to use these big frameworks? And that's where the final API that I'm going to talk about today comes in, view transitions. So you kind of saw a little bit of this on the video that I played before. This is my website. If you tap on one of these videos, you'll see that you get this nice animation between the two. It's very basic. I'm sure you can do more creative things than I do with this. But this is just a regular old website. It's not anything that's a real single-page app or anything like that. And you get those nice transitions. It doesn't feel like an actual website anymore, almost. I mean, the design does, but you could use this within more of a web application UI. So what view transitions are, again, declarative API used for transitions within pages. So you can use this with single-page apps. Or between pages, so you can use that on those regular navigations as well to give this kind of seamless, like fluid app-like experience that single-page apps kind of claim to give, and generally they do, but there's a lot of overheads and a lot of trade-offs when you implement those big JavaScript frameworks. Again, it's a very simple API. If you want to use this, the level 1, where it's within a page transitions, 1 line of JavaScript. If you want to use cross-page transitions, 1 line of CSS. And you can make it more and more advanced from there, but this is the very basics. So hopefully I can just inspire you to go and look at this stuff yourself. So this is your JavaScript. So literally call document.startViewTransition, give it a callback, and then just make some changes, and it will handle the animation for you. If you want to do it across documents, this is your CSS. Literally, you could put that on 1 line. It's 3 lines, but 1 declaration. And technically, you could just stop here. This would create like just a fade between the 2 pages. If you want that kind of transition of like the video moving, for example, then you just need to give it a name, basically. So there's another CSS attribute. So technically, more than 1 line if you wanted to go that far. But and then you can customize all of the like animation keyframes and things like that using just regular CSS keyframes. So all that knowledge, that web platform knowledge, kind of compounds here. In terms of when you can use this, level 1, like animations within a page, single-page app style, you can use that today. It's in every single browser. Level 2, we're still waiting on Firefox, but again, it's a progressive enhancement. Those browsers that don't support it just get that immediate kind of flash between the two pages, and they don't get that nice animation. But the benefit here is that you get to offset so much JavaScript. You don't need those massive frameworks to give that really rich experience. So this is where the web platform APIs really excite me, because we can combine these things together. We've got compression dictionaries reducing that overhead. We can hide latency with speculation rules. And the benefit there of combining those two is that our accuracy can be a little less specific. Like if we're a bit more concerned about, okay, well, we don't want to load so many pages because we're wasting bandwidth there. Well, like with my site, pages are 4 times smaller if they're with compression dictionaries, so I can effectively load 4 times as many and not worry about that accuracy so much. And then we've got view transitions, so we get that more cohesive UI. And that means that we don't need as much JavaScript, which means that when we do load those pages with speculation rules, that we get more instant page loads because they're going to load faster. There's less to download into the browser. So all of these things kind of combine together. They add value in isolation. You can very much go on this journey. But as you adopt more and more of the web platform, these benefits start to compound. So, just to summarize, for my entire career, JavaScript has been a bit of a problem. And we've kind of doubled down on this over the past decade. The thing that's been hurting us, we're now using more and more. And when you start to monitor this stuff, you'll start to see that LLMs aren't saving us from worse law. They're actually, turbocharging it and making it a little worse. So, the web platform has been doing its best to hand us the tools. Jack mentioned that this morning. Like, literally, please learn the principles of the web platform, your HTTP, your HTML, your JavaScript, your CSS. Even if you you might use things like Tailwind, or you might use a framework, knowing the underlying features of how the web platform works is always going to be valuable knowledge. So this is our counterweight against this growth. Like, lean into it. Not because it's kind of virtuous, but because our real users, the ones that we don't really think about when we're sat in our home offices or in the office on our gigabit fiber connections, on our brand new MacBook Pros, on our latest iPhone, the people we don't think about are the ones that pay the price when we don't think about this. Thank you.